Alright, so for this video, we're going to talk about determining spontaneity of a reaction using a standard reduction potential table. So this is the same table you'll be getting on your exam. Maybe not exactly this one, but one similar to it. There's an earlier table in the booklet. Right now I'm on page 26 of your table, of your booklet. So in this, the lesson as originally written used a rule of bottom left to top right. As long as you're combining them, you could guarantee a spontaneous reaction. And later in this unit, we talked about the potential of the half reaction for different elements, and typically in the reduction potential. So this is the potential energy available if an element is able to collect extra electrons. Different elements want their electrons either more or less. A positive value for the potential means that the reaction is favorable. So for example, on our left over here, right at the top of this table, we see fluorine. And fluorine is a very strong oxidizing agent. It steals electrons very well. So here at the very top of the table, we can see fluorine gas goes from pure element state 0 to -1 as a fluorine ion, and the potential energy is 2.87. It's the most positive one on the table. This is also connected to electronegativity that we covered back in our very first unit. Down at the bottom, lithium, one of the least electronegative elements, has a negative potential. This means it's very unfavorable for the lithium to become reduced. For lithium ions to become lithium metal, it's very, very unfavorable. So we get a negative value for that one. So what we want to do is we want to check to make sure that on the left of our reaction, so for example on the left here we have magnesium and we have tin metal. We want to go and check those reduction potentials. So I'm looking on my left here for magnesium. Notice magnesium metal is way down at the bottom. Maybe I can just drag this and put it here. I'm just a little worried that it's gonna throw everything off here. Where did it go? Oh, okay. It is there. Oh, okay, it kind of worked. So I can put this up here. Okay. So magnesium metal is way down here, and it's on the wrong side in a way. It's well, maybe that's favorable. So let's just check. So magnesium metal is negative 2 point. Oh, actually, sorry, just 1 second. We know something about this. When we're using the potentials of a chemical reaction, if the element we're starting with as the reactant is the product of the reduction, that means we actually are going to be talking about the reverse reaction. So magnesium here is the product of reduction in this standard reduction potential table. So for the reaction to proceed in the reverse direction, it will have the reverse potential energy. So this has a positive 2.37 potential. And then let's go find tin. Hopefully tin's on this series. Uh-oh. Anybody see tin here? Is that tin? It's not. Yeah. I don't see tin on this list. This will be very, sort of defeat the point if we can't. Yes, but that's magnesium ions that are negative, right? We are reacting magnesium metal. So if it's magnesium metal, that's the product of reduction. So this magnesium metal will be undergoing oxidation, which means that the potential will be the reverse. So that's why it'll be positive. So that's important. Now, I don't see a tin on here, so I'm gonna slide up here and see if I have another tin. Oh, I do have one here. So I do have a tin up here, and I have a tin ion here. So that tin ion one is in the correct direction, so that's negative 0.14. And as long as these two numbers will add up to a positive number, the equation is considered spontaneous. The reaction is spontaneous. So adding a positive 2.37 and a negative 0.14, that's a positive reaction. So that is a spontaneous reaction. You should finish up balancing this. So in this case, we're going to exchange those two electrons and proceed. Alright, so let's try to find one that doesn't work. So let's see if we can find one with maybe zinc. This is not the best table in the world. There's a zinc down here. Negative 0.76. So if it's zinc over here, that one, okay, so zinc metal, so that means I'm going to reverse it. Because on the table, it's for zinc ions. I don't have zinc ions. And the tin ions are the same ones I just had, so those are also negative. Combine those values, you still have a positive number, so the equation is still spontaneous. Yes. So let's see, do we have one? I'm thinking ahead to see if I can find one that will not work. Yes.
What if we do the first one, question A? Because the rule we did in class and the rule we did in this is like a little bit different.
Okay, let's try this one down here. So, do you mind if I just do this one example first? So here's copper 2+, so I'm going to find that on my table. And I'm going to assume that I'm going to try to reduce it all the way. So I did see it just a second ago. Copper 2+. Minus 2 point. Copper. Yes, this one here, right?
Yeah.
So this 0.34. So 0.34. And then the tin is now tin metal, right? So earlier we said tin was negative 0.14, but that was for the ion form. Now you're talking about the metal. So is it going to be negative 0.14 or positive 0.14? Isn't it? There's two. You gotta watch out. So if we're fully reducing the copper, then we have to use the full reduction of copper. So that's the full potential of copper. Copper can be reduced to the +1 state, or it can be reduced to the +2 state. How do you know which one? That's a great question. I'm going to I have always used the full one. I'm sure there's a better answer than just this is what I've always done. But yeah, what is the answer there? It will work either way. It'll be pretty tricky, and then you could take that. I think we have to. We're going to assume that that a metal is going to make another metal, kind of thing. So we're gonna take the full reduction. I can't really think of a good example where this is gonna be the case. So I'm gonna use this one. I don't know why. That's just the one I'm most familiar with using in this type of situation. And I was really looking for one that was not gonna work. Okay. That one works fine too. Zinc metal, that's gonna be okay. This one will, okay. I got it. I found it. Okay, G. G is the one. We should probably finish this one up. Here's their copper metal. And again, tin. It's always nice to work with things that have the same oxidation state on both ends. Alright, so G is the answer. So G, I've got the metal. Well, it's not the answer. It's gonna be maybe make more questions. So I'm using the metal. Normally, a reduction would be -0.76, but in this case, it's oxidation, so I have positive 0.76. So far it sounds good. That sounds like it's going to be in our favor. But if we go look up the sodium reduction potential, starting with the sodium plus ions, that's this one here, we see negative 2.71. Yeah. please.